Our next speaker is Bennie Ward. He is currently a distinguished professor of physics at Baylor University in Waco, Texas, and he's currently on research leave as a visiting professor of physics at the Werner Heisenberg Institute, a Max Planck Institute in Munich, Germany. He received his PhD in physics from Princeton University under the direction of Sam Treman, and he has authored more than 290 papers in the theory of elementary particles. He's focused most recently on precision theory for physics objectives of the high-energy colliding beam devices, such as the LHC at CERN. He also has worked recently on quantum gravity and the cosmological constant using a theory he created that he calls resummed quantum gravity. He's a fellow of the American Physical Society. He was the founding associate editor and is currently the editor-chief of the Open Physics Journal, which helps to avail refereed publications to members of the developing world. So he'll tell us today about yesterday's science, standard model quantum loops becoming tomorrow's engineering applied mathematics, how resumming loops from yesterday allows observation of new loops from tomorrow.
Thanks to the organizers for giving me an opportunity to talk, and I guess I'll know if I'm really thankful after I finish the talk, because the title, as you have seen, I've already made a reinterpretation thereof. And I noticed on the website they've changed the title even again. So in fact, if you look on the website, you will not see this title. But let's see how it goes. So one of the most important one of the most important things I want to do in this talk is to try to pick up on something that Mike Peskin actually did a lot better job of than I had expected. So he's actually done quite a bit of the work for me. But I'll refresh your memory, because it's actually rare that these remarks are included in these types of meetings. And so in the reinterpretation of my title, I'll look at the theory a little bit more detail that he talked about required to remove the big corrections from these very large data sets, so that you can see the new physics and the fact that the standard model electroweak loops are actually observed in the data. And I'm going to give an example, and again, Michael, as usual, has even managed to come up with information, again, that's going to be on my slides. This is historically the case. And but nonetheless, I will do it, because again, I think it's very important, as he was trying to say. So I use the LEP case to show the example of what I did when I reinterpreted my title. And really, therefore, to try to give some basis for saying that we really have a modern version of a intellectual achievement of the human race that's on par with what was done by Newton and Heisenberg and others. I mean, it really is true. And therefore, in the other parts of the talk, if I have time, I'll make some comments, as he did, about what might come in the future. So this is the way then that I have attempted to take my charge, namely, the yesterday's science will be the Yeni-Fauci-Sur type resummation theory, which I have here, and also similar types of resummation algebras were invented by Professor Weinberg, both for quantum electrodynamics and for quantum gravity. And the application, the applied mathematics, if you want to call it that, ends in reality in this talk, Weyfeld-style resum Monte Carlo invention generators that Michael made some reference to, for precision studies at high-energy colliding beam devices, and I'll give the examples from LEP 1 and LEP 2 But of course, the future shows that this will be playing, this story will be continuing through the era of the precision science in our field. Now, so let's see, I'm going back. There we go. Let me just, Fritz Behrens has already been mentioned, I think also by Michael, but I want to put him in this meeting because in the 1988 Rochester meeting, which now if I would be going this summer would be 30 years ago, he and I were having, in the conference banquet, he and I were sitting next to each other, and we were arguing about the question of how accurate, we call it exponentiation, but how accurate could we make the resummation of what would be yesterday's quantum loops, i.e. QED. QED was considered the theory that Richard Feynman and Schwinger and Stammenauer had understood, and the only question was to calculate the theory. And the question that he and I were arguing was, should we just go exact loop by loop, one photon, two photon, as we need it, or do we need to take part of the theory in a systematic way and resum it? He agreed we needed to resum it. There were two ways of resumming, the so-called Jackson-Shari approach and the YFS approach. And then roughly speaking, in Jackson-Shari, you just isolate the largest corrections order by order and resum them as an overall factor, and you really don't control very much the differential spectra associated with what that's multiplying, except for its integral. You require that the integral is there, but not the differential spectra. Whereas in the YFS approach, you keep the entire amplitude series at the differential level, at the amplitude level, order by order, in the presence of the resummed large terms. And that's why the Monte Carlo event generators that we made and that Michael referenced can achieve sub-per-mil and even below that, as I'll indicate, accuracy, because we really haven't given up the original series in any way, form, or fashion. Now, this discussion today, which I won't have a chance to talk about, has an extra dimension to it, because in the history of the QCD applications, which I'll mention if I have time something about, they have had the history of putting in a hard cutoff. So in the whole idea of the resummation was that in the soft regime, we summed up all of the large corrections, whether you do it with JS or YFS or Weinberg. And then you therefore have that part of the theory smoothly under control. In the QCD, the history has been to resum the collinear parts of the theory because they're so large, and to just put a hard cutoff on the soft radiation. Now, the errors in QCD calculations have until recently been several percent, so that whether you have the hard cutoff or not has not been a big deal. But now that they can make, as I will show, QCD measurements at the percent level, the experimentalists can, this hard cutoff is going to have the same outcome as it did. We couldn't use a hard cutoff for the infrared in QED, and we're not going to be able to use one in QCD either. But I may not have a chance to go into that. So I just want to stress again that we therefore have both parts of the SU2 left cross U1 theory, the QCD part at sub 1%, as Michael was trying to indicate, and of course we all had the sub-per-mil electroweak theory for some time now. And this is the approach that the YFS inspired approach, amplitude-based resummation theory. In the presence of QCD, we have to match it with parton shower Monte Carlos, in which Michael has also mentioned. It's good to have Michael before you. And so therefore you can have, if any given level of exactness, he was talking about MC and NLO, but there soon will be an MC in NLO, et cetera, that will continue. And the thing that we're trying to convince people of is that this amplitude-based resummation is the best way to do this. Now, we have not succeeded to do that yet, but it took us a while to win out at lab also, so let's see how it goes. These are some of the projects, therefore, that are underway in this regard, and this is just, you can look at these up on the transparencies. I don't have so much time, so I won't go into this, but we have demonstrated these effects and comparing with existing LHC data. This is the program that Michael was talking about. We have the improved versions of it for Pythia, et cetera, and you can study these offline. And all the data starting from, these are in CDF as well as Atlas CMS, we see that the improved analog of, so in other words, we take this Wi-Fi style resummation that we invented for Lab 1 and Lab 2 and take its analog to CERN for LHC and FCC physics, and we see that the data, even in the forward direction, I'm sorry, for the LHCb, are improved compared to what you get if you don't. Now, we have also managed to take the electroweak theory that we had into the hadron environment. This is KKMCHH, Michael. He was talking about Coral Z. This is the modern day upgrade of that to the CEX style amplitude-based fully coherent treatment of the effects, and we are the only people right now that can really control this level of accuracy on the electroweak corrections at the hadron colliders with in a hadron environment. And so what we'll try to do, and what I have time left, will be to show how this title I was given, Yesterday's Science Becoming Tomorrow's Engineering Applied Mathematics, help to facilitate the proof of the standard model paradigm that we are celebrating today, and how, as Michael was trying to indicate, as we go to these new machines, let's assume we'll get one. He mentioned the Chinese machine, and I think he mentioned the Japanese machine, but he didn't mention, if I recall correctly, the FCCEE. So let me mention that, which is the one that might happen in CERN. Now, and this is what we're talking about. Today, we've got 50 years of the brilliant paper by Dr. Weinberg, Professor Weinberg, and 45 years of the QCD of Gross, Wilczek, and Politzer. And this is where we hope to be headed. This is a 100 kilometer tunnel. This is the LHC, and you can double energy of this. There's a version of this slide with the high energy LHC on it, but this is an earlier one. And as you can see, you have 16 Tesla magnets in there and 100 TeV-PP collisions. And the time scale is, 60 years, which, by our standards, is not so much. It's not so much. The cost, 30 billion of something, whether you're now this is the theory. Here we've resummed out in front, and if you were doing Jackson-Charriot, this would then be your sort of average cross-section, but you say I don't have an average cross-section. I actually have the actual quantum differential distributions for any number of photons and gluons. And that we have put in the Monte Carlo. Okay. That we have put in the Monte Carlo. And so these functions are all known, and in the QCD theory, they may be continued to higher orders than alpha if you wish, but that can be diminishing returns, so you have to take that into account. The shower matching is indicated so that you can connect with all the known showers after you improve their infrared point, which is also something we know. So I won't I won't spend so much time on that because I want to get to the connection with today's meeting. But you see, this is the basic formula. This is your heart cross-section and the distributions. And if you want to make contact with the formula, the program, as Michael was indicating, these are the well-known distributions that you need to put with the corresponding pseudocofactors as indicated by the delta Monte Carlo. And the pseudocofs control the large collinear effects. And in the infrared point, as I was saying, I don't show it here, but most of them, well, here you can see, most of them have just a hard cutoff. And what we do is we are improve that to get something which therefore would not have in principle any problem of the kind I'm going to try to indicate before the talk's over. And if you want to make contact with our theory, it's algebra that we know how to do. And you can do this in the so-called Powhag realization, where the first emitted gluon is required to be the hardest one, or you do it in the program that Michael was talking about. It doesn't matter. You can also do it in the KRKNLO approach, an analogous approach invented by my colleague, Professor Yarek in Krakow, in which one doesn't have so many, one doesn't need, where am I at? One doesn't need the contacts terms associated with the usual prescription because of the more use of the YFS approach from the beginning of the process. Now, the idea is that, therefore, theoretical physics is required to make contact with these precision data. Here is the connection with the CEX order alpha squared L that is now the state of the art in the electroweak hadron Monte Carlo. And I don't, the precision without going into the hadron beam is something we were using in LEP, KK Monte Carlo. If you read those LEP papers, you'll see it's used extensively there. And now what we've done is carried that over to the LHC so that this is again the CX realization of the amplitude resummation theory again. And the electroweak theory, from the pure weak part of it, we can take it from Halleck's library or from Bardeen, again, somebody that Michael has extensively referenced, and these are just making sure that the beta 1 pure weak corrections are done exactly to order alphas so that we can tell if they're actually in the data. Now, and I'll get back to why I show you this in a moment. And this then is the formula that we already had, where these are the distributions, and this is now just doing this, but now in the presence with the photons and gluons in the game. And that's a Drouin process, so the protection of a Z on W with lepton pair. In fact, in this case, it's just for Z. Now, here's the scenario that I want to focus on. And this you can see more of this in a talk by Yannick that was given recently. You have the experimental data over here. So this is what you build the 30 billion, or in the case of LEP, it's not. I mean, LHC is not 30 billion, but it's a few billion machine. And you get data cutoff dependent. They have all kinds of QED effects in them. Michael showed you how big the effects are. The typical logarithm, if you're in the Z region, is 10%, just the log with the alpha over pi in it. And if you go on the resonance itself, this thing is getting amplified by the rate log of the ratio of the width to the mass, and you're talking something of order 1. As he showed. And so you have to, this is an infinite order problem. You don't get to, if you want to have sub-per precision, which he also showed would be what normally would be the natural size of the pure weak effects that tell you whether the Tuff-Veltman renormalization program is the correct one or not. You need to be able to measure these per mil level effects from these large, highly affected data from large yesterday's loops, i.e. QED, and so you have all of that over here, and so you have to somehow, and we use Monte Carlo event generators as I just described. You have to remove that so that you get to what we call a pseudo-observable, which is the cross-sectional asymmetries and partial without the QED in it. You have to remove that. And then you go to you take the one loop corrections from Bardeen or from Brian and Robin, or, which we did also at one point, or Hollick, and you can compare this to these deconvolved data. So you're trying to see a per mil level prediction where you have removed effects, some of them of order 1 from the data. This is what you're talking about. You have to control something getting close, in some cases, to 1,000, a factor of 1,000. Theoretical physics is being required to do that. And if you find, as he was also indicating, if you find at the end of the day you don't get a match, he showed that you would then be able to put constraints on new models. I knew it was very dangerous when I saw he was talking before me. I knew that this would probably happen. Now, and this was worked out in the case of in this nice paper here by Bardeen, Grunwald, and Passerino. I don't think he mentioned Grunwald, but he mentioned Passerino. The question we're facing now that we were trying to present in MPI a few weeks ago, Yada, is that actually we have to do something more than this for these FCCEE, these type of machines that want to drop those precisions down, as he was indicating, by studying those things very precisely. We have to go a little bit beyond this, but I won't have time to do it. I want to stick with LEP 1 and LEP 2, where it's happened, where we're talking about something that's happened. And he also had at least part of this showing, I think he had this first part, how much of a correction we're talking about. This is the data and the theory of the kind that I just showed. And this is what happens when you take the QE out of it. And you see, this is the type of thing that has to be controlled to the per mil and sub per mil level. And this is the cross section, and on the asymmetries we have a similar interplay. See, this is what the data looks like, and you have to take the QED out of that, and then you get something that you can just use to determine whether the loop corrections, as predicted by the Tuff-Veltman renormalization program, are actually correct or not, or do they allow for some new physics? Now, these are this is a list, this is not all of them, a list of the precision observables that one can look at in the Z region. We see the line shape, the mass, the width. This is supposed to be gamma L here, the ratio of hadrons and leptons. The number of neutrino species, the sine squared theta that he talked about. This was his statement about what was their, what were they saying? That, of course, they did not do this well at the beginning, but now I think this that's present, so this is something that has been released recently. And what you see in curly brackets is how the QED that I'm talking about removing, how big it was in these digits here. And you see that we were focusing on a couple of them for a few weeks ago, but in general you see that you cannot really, if you don't control these things, you don't need to build the accelerator. That's all there is to it. There's no point to build it. Now, in this machine of the type he was talking about, which will be we call it the he just has FCC, but this really should be FCC-EE. This would be a machine that can run in the Z and Higgs region that he was talking about. And you see the kind of improvements that the theory community is going to be asked for. And in one case, far-back asymmetry, even though we already have a very precise result for level 1, this new machine of the kind he was talking about will require us to improve that by a factor of 100 compared to what we currently have. Now, just to illustrate a little bit, if I look on the invisible width of the Z, you see the hadron cross-section is sitting there in the formula. And therefore, it means that if I don't know the normalization of the accelerator, I can't measure the number of massless neutrinos. And this is the way the error enters into it. This is the luminosity error. Right now, we ended up with BH Lumi at 0.061 in this paper, but Opal actually got it down, making some further correction, 0.05. 3, I think, 0.54. That will need to go down to 0.001 to take advantage of the similar kind of study in the FCCEE or the CEPC or this linear collider that can run this physics program as well. This gives you an example of what we're talking about. And so lately we have been asked by CERN to make a public statement on that, and it's in the works. And as you can see, we're putting our neck out there, and we're pretty sure we can, with proper resources, which theoretical physicists do need, contrary to popular opinion, we can make this happen. Now, all of that was going on in the time of CERN. And here's an example. He also talked about the YFSWW. You've seen that. This is the Raccoon WW. And we're comparing these two programs. These have the Tuff-Veltman one-loop corrections in them, and they have the resummation of all the large QED effects independently done. And you see that the ratio of the experiment to the theory is very good. And if you take out the Tuff-Veltman SU2 left cross U1 one-loop correction to this process, which he described the effort required to get that by Doreen and others, if you take it out, this ratio drops down to almost 4 sigma disagreement from this beautiful agreement we have in the Monte Carlo comparison to the data. And so this, therefore, is why the Tuff-Veltman renormalization program can be said to have been observed in the experiment. We can actually say that. And I just show one observable, but we could go through this for all of the precision observables. If you don't put the Tuff-Veltman electroweak, pure weak corrections in there, so this is beyond QED, the part that they added beyond Schwinger and Feynman and Tomanak. If you don't put it in there, you're looking at 4, in some cases 5 sigma discrepancy between the precision Monte Carlo realization compared to the data. And the Nobel Prize Committee has made a thorough investigation of all that. Similarly, if we look on the question of the QCD corrections in the precision data, Michael was pointing out that because the data are so precise, they also end up constraining alpha S effects, because using this formula taken from Antonio, you see the ratio of hadrons to let's say E plus E minus into the zeta leptons. Okay, this is something that Tuff-Veltman theory, which I just argued we have proven is correct, okay? And then we have the QCD theory that Gross he left, but Gross is responsible for, and Wilczek and Politzer, and this is known, this series is known. And so if you, at the PDG, have inverted this with this very precise number at the Z-pole, and they quote this result for alpha S of mz squared. And now if you look at the plot showing how alpha s is running according to the prediction of asymptotic freedom, you see this point is sitting there at 90 GeV, and it fits 91 GeV, and it fits beautifully on the curve, giving a beautiful chi-square to the fact that alpha s really does run the way that Gross, Wilczek, and Politzer have predicted that it runs. And this is, again, not possible if you leave out these large corrections on the hadronic cross-sections that Michael was talking about. If you don't control them at the subfermil level, you simply can't you can't make this conclusion. You just simply can't do it. Okay. Finally, going forward, and I will make a, since I'm not complete out of time yet, but I'm getting close. Let me just say that at the 100 TV machine, all of these corrections, the higher order corrections, you see, it's extremely important not just to know a formula, but to know how to use it. These top points don't have the right scale. They have a naive scale for alpha s associated with half of the Z mass, or the Z mass, which would be appropriate if you were not making extremely large PT. But you see, I'm making PT of 1 TV. 1 TV is a small PT on this plot, and we're going out to 12 TV. So we're looking for the states that Michael was trying to talk about, the ones that so far we haven't seen in the LEs for new physics. And you can't do it if you don't control properly the precision calculations. That's the message of this plot. And here recently, and then I'll end, Atlas has put out the most accurate measurement of one single experiment last year in the history of our civilization for MW. By just one, I'm saying, one, not combined, but one. And in there's a modeling error of 14 MeV. This whole thing combines up to 19. There's a modeling error. And in this modeling error, there's about a 7 or 8 of those MeV associated with these higher order effects that I'm talking about. And so this is the reason that we have introduced this order alpha squared L correction. And as you can see, if we now interplay that with QCD, which is what this plot is showing, so this is in the context of the hadron Monte Carlo that has the order alpha squared L with a Hurrig or Pithier type hadron Monte Carlo. You see that there's a significant modulation in the regime where most of the data are. And so you have to do this. And it has to be done correctly, because if it's not done correctly, you run the risk of not discovering the kinds of things Michael was talking about, wherein you have a small deviation from what, let's say, tough development theory would tell you should have. This is the message of this plot. And so I'm finished. I hope my reinterpretation of my title wasn't too drastic. But I claim this is, and I think Michael tried to indicate this is a continuing story. There will be the story of today's technology, engineering, applied mathematics being yesterday's science. If we don't get it right, if we don't hire the young guys and women that do this type of work, if we don't say they deserve a professorship, anybody off the street, you just bring in somebody off the street and let them run a Monte Carlo. That's all you need. If you do this, you run the risk of missing new physics. And I didn't have time to talk about it, but even the quantum gravitation theory seems to want us to do this thing. So I end by saying, why not? Thank you very much.
So I'd just like to make a comment on one of the points you made.
Okay.
You emphasize the extreme levels of theoretical accuracy that you need to take advantage of the extended Z program at the FCCEE. And this is extremely challenging. However, something that I probably should have put in my talk and I forgot about, but I have a chance to correct myself now, is that Eris Freitas at Pittsburgh, Tord Riemann at DAISY, and their collaborators have recently completed the actual complete two-loop
That's right.
precision electroweak analysis. A couple weeks ago at Pheno, I asked Eris whether he was ready to do the three-loop calculation. And actually, he thought that it was totally feasible with the required computational resources.
That's right.
So I think one can actually get there on the theory side.
I agree.
And the experimenter also, the systematic errors that you need to combat are extremely difficult. But maybe we can really get there and do this program.
Yeah. Thank you very much for that comment.
Okay, let's thank Benny again.